usually EV, it is simply a two-level, three-phase inverter. So very conventional 6-switch inverter they use. All the switches could be silicon carbide. They're even proposing to use gallium nitride. So switch could be silicon carbide, or even gallium nitride. Okay, but this topology is just two-level, three-phase, 6-switch inverter mostly. Okay, and we could have a DC-DC converter. We talk about this is again quite conventional to bidirectional DC-DC converter in the commercial vehicles. Although there are research to improve this, there is also research to use some multi-level converters, etc. So in this system, if we look at how the speed, torque, and power changes in an EV, you can see it here. This is the urban driving cycle. This is highway driving cycle, right? Or one is for the speed versus torque characteristic here, and same thing also for the two different cases. Okay, and you can see how in urban driving or highway driving speed changes, right? This is speed, car speed versus time. Okay, so you can also see how torque changes, speed changes. So to achieve this torque speed change, we must have proper control, right? If we only have the motor, it's not enough. The motor drive, you must control it sufficiently so that you can have the smooth ride that we experience in the IC-driven car, right? So this part, that's why first we will be looking at the control. We will start with classic P/F control, and then we'll move to how the concept of flux weakening and constant power is in classic P/F control, and then we'll probably move to some more advanced ones, okay? FOC, field-oriented control, or DTC or MPC, etc. So today's talk actually would continue to tomorrow. So let's look at this power and torque equation that we have discussed previously. This is the classic equations, right? And in this classic equation, perhaps most of you know that you can get a constant torque, constant maximum torque in synchronous machine. But if the delta angle is, if the delta angle is 90 degree, we get the maximum torque, right? In a cylindrical or non-salient pole synchronous machine. And speed depends on your frequency. That is like it is always synchronous speed, so speed is your frequency. Now if I want to change the speed in a synchronous machine, I have to change frequency, right? And that's what you do with your inverter. You're changing your frequency to get different speed. Now if I change frequency, let's look at this classic equation. If I change frequency alone, what is going to happen? If I only change frequency to get different speed, what will happen? Your reactance, synchronous reactance XS is also going to change, right? Or XD. These are all omega time inductance. So if you change frequency, your omega going to change. So this reactance is going to change, and your back EMF is also going to change, right? Because back EMF is omega time flux linkage. So if omega changes or F changes, then this quantity is going to change. So in our torque equation, let's say this is the torque equation here. If I only change frequency to get different speed, this quantity going to change and this quantity going to change, right? So I'm not going to get the same maximum torque, right? So how do I get same maximum torque at many different speeds? I want to get the same torque at many different speeds, right? Only then it makes sense. So how am I going to get it? And that, how to get maximum or same maximum torque at any speed actually takes us to the concept of constant V by F, right? So those who have done drive courses, maybe you are familiar with it. So in the same torque equation, we can, let's rewrite it a slightly different way, okay? So back EMF over omega this omega and back EMF, right? So this ratio of these two quantity is actually your flux linkage, right? Because flux linkage tan omega is your EA. So ratio of EA over omega is the flux linkage. And in case PMSM, it's a constant value, PMSM, flux linkage of the PM or magnet. So if EA over omega can be, this is a constant. So even if we change omega, that means EA is going to change proportionally, so it's kind of constant. But if we change omega, we still have problem with the synchronous reactance part, right? So let's expand that synchronous reactance as 2 pi FLS, right? And then this is equal to 2 pi FLS. So this frequency component, we can then make it as a ratio of V over F, okay? And keep the 2 pi and LS part out of it. So now if we look at this equation, if I change, when I am changing frequency, if I change the voltage also proportionally, my terminal voltage proportionally, then I will always going to get the same constant torque, right? Everything will remain constant, even though we are changing frequency. Even though I am getting different speed with different frequencies, since I am also changing voltage proportionally, so I am always going to get the same constant torque, right? Any questions here? So same torque equation, we are just rewriting it differently, right? EA over omega is your magnet flux linkage. Okay, this is equal to magnet flux linkage in the RMS value. So lambda PM is your peak value. That's why PM over lambda PM over root 2. And VA over XS, this part we can also write as VA over 2 pi FLS and VA over F. This ratio, if I maintain constant, I will always get same maximum torque over any frequency. Okay, so this is the concept of V by F control actually, which is common for all three-phase machines: induction machine V by F, synchronous machine, PM synchronous machine. Also, you can do V by F if you want. Okay. So by changing this ratio or keeping this ratio constant, I can get for any speed same maximum torque. But there is some problem, although theoretically it is true, like I can get the same maximum torque for any speed up to 0. But usually that's not the case. If you have done some experiment, you will see that you do not get the same maximum torque at low speed. Very close to zero speed, you cannot get the same maximum torque. Do you know why? What's the problem with low speed? I'm keeping V/F constant, running the motor, but at close to zero speed or very close to zero speed, or let's say 5 to 10% of the rated speed, and I can't get maximum torque if I don't do something. Sorry?
I mean, the
Magnet flux linkage is constant.
But the rate of the speed change the flux is not that is change. And phi, d phi by dt.
Yeah, so n d phi dt, right?
Yes, that will change.
So n d phi dt is, we write it as a lambda Pm over dt, which is your EA, right? So EA will decrease. But EA we are writing, we can also write it as a omega lambda Pm, right? Omega lambda Pm, right? Now what we have written here in this equation is that EA over omega is lambda Pm, right? Lambda Pm is not changing, correct? Lambda Pm is constant. So with speed lambda Pm is not changing. Okay? So what happens at low speed? Why I can't get maximum speed? The reason is, main reason is when we have developed or when we have find this power equation, remember? We have ignored resistance. Okay? We have ignored resistance. We said that resisted drop I times R is negligible compared to E, the back end, right? But at low speed, this EA is low, it's small, right? And EA becomes somewhat comparable to IA, I time RA or I time R, okay? So ignoring R doesn't actually is any more correct assumption at low speed, okay? So at low speed, that's why if we only keep V/F constant, we will start to see torque falling, okay? Torque will start falling. But we can prevent it, okay? We can prevent it. In fact, we can, this is, I'm going to not talk about it too much. This torque equation, you can actually derive it. Assuming resistance is not zero, okay? You can find a power equation, and from the power equation you can again calculate our constant torque. And in that torque equation, even if I keep V/F constant, I am not going to get actually same constant torque anymore, because the torque equation changes, as you can see, okay? It's no longer same as what we have found previously. Because we have an extra component, this resistive component is present in our torque equation, okay? So that our previous assumption of V/F constant gives us constant torque is no longer true here. So what can we do is, in this type of situation, we could actually boost the voltage, okay, boost the voltage by the drop I time R, okay. Previously we have only V, we are increasing the voltage in proportion to frequency, right? But at close to zero speed, we will keep this ratio constant, but at the same time we will actually have the voltage slightly higher, okay? So that's, we boost the voltage by this drop equal to the resistive drop, I time R. Okay, so you must, if we do that, we can prevent the torque falling too much at a low speed. And you can implement this type of control, P by F control, relatively easily, and it's a kind of simpler torque implementation because we can do its open loop. Okay, so you could have a speed controller, or not speed controller. You could have a speed command. So all open loop. Okay, there's no closed loop control here. So you have the speed command, and from the speed command you can determine what is your frequency. Okay, because your speed is your synchronous speed. Speed is the frequency, since it's synchronous motor. So you know what is your frequency for this particular speed command, and then from the ratio of the rated voltage and frequency, F naught is, let's say, rated voltage and rated frequency. So we know this ratio. So for any frequency, I can increase the voltage or decrease the voltage in such a way that this ratio is always maintained. So from this ratio I can calculate out what the voltage I need for F1 frequency, right? What's the voltage I need if my speed relates to F1 frequency. So I get that voltage, but if for low speed I will add an extra voltage to my voltage command. So N is that ratio. This ratio we can also rewrite as P naught over P1 F naught over F1. So you can also write like that. So this is how it was written here. And so we get these, we could have a lookup table sort of things, okay? And we get this voltage amplitude command here and frequency command here. So these two together can give me my reference voltage for PWM. Okay, remember for PWM you need a reference voltage which you modulate with your carrier signal, right? So this voltage and frequency, with that you can construct a reference voltage for your PWM signal, and that becomes your, PWM signal will go to your inverter, and you could run the motor according to P by F control open loop. Okay? But there is always a but. This P by F control can also give us actually also fluctuating. Okay, before I show you the issues, but with P by F control we can also get fluctuating easily. Okay, remember you are increasing your voltage with your frequency because of the P by F control, right? But you cannot keep increasing your voltage infinitely. You can only increase your voltage up to the rated voltage, right? So once we have reached the rated speed and rated, so that our voltage is now rated voltage, right? After that, I cannot increase my voltage anymore. If I want to still increase the speed, I have to keep the voltage constant. But frequency will still increase, right, if I want to increase speed. So that means what's going to happen now, this frequency is increasing, but voltage is kept constant in your torque equation. So torque will start to reduce, right? That's what we want. Torque reduce, speed increases, constant power or flux weakening, right? So in V by F, you can simply keeping the voltage fixed at your rated value at high speed or at a speed beyond rated, you get flux weakening directly. Okay, so this is also can be achieved quite simply. Okay, but the issue is in this type of control is that it depends on the steady state equation only. That remember this equation was developed from the equivalent circuit, right? This equivalent circuit we used. This equivalent circuit we used to find that torque and power equation, right? But this equivalent circuit is valid only in steady state. We cannot use this equation or this circuit in transient condition. So V by F only can control the motor at steady state. It cannot do anything during the transient. So during acceleration and deceleration, you have no control. Okay? You have no control. So that's the biggest issue with classic V by F type control. We can also use, based on the same steady state equation, a current control. Okay, we could do current control too. So to understand current control, you may want to look at this vector diagram here, okay, or phasor diagram of the voltage and current. The power, like you may remember that the main power, that is which contributes to the torque, which is sometimes called as the developed power, from the basic of DC machine. That developed power is back EMF, E time I, right? So it is the same concept. Here we can also think of that back EMF E time current I is your mechanical power, even in the synchronous machine, right? But because they are not DC quantities, they are AC quantities, so we have to represent them as the phasor diagram or vector diagram. So I also mentioned that your back EMF is usually in your Q axis, right? And magnet flux linkage is along your D axis, if it is in D axis. Now, where will be my current? Okay, where is my current? So current either could lead your back EMF or lag your back EMF, right? It could be either in this quadrant or that quadrant. Okay, so here let's say I is in the first quadrant. So we are getting a positive ID and positive IQ component of the current, right? And but there is a phase angle between current and back EMF now, right? Current and back EMF has a phase angle of, here let's say we describe it as gamma. So this angle gamma is called the current angle, okay? So the power E time I is actually, in case of a three-phase AC synchronous motor, is E time I time the power, the phase angle between E and I, which is in our case cos gamma. Okay, so this is also the power equation. Okay, this is also the power equation from steady state average power. And dividing this power, we can get torque. So basically, if we can control the current and this angle, we can also vary the torque, or we can change get the different torque for different speed. Okay, and because you can see here this EA over, in this equation, EA over omega is again a constant, right? And by varying so if I change frequency, there's nothing that will change in this torque equation. If I keep current I and cos gamma fixed, right? I can still get a maximum, I can get the same torque at different speed based on this equation. If I want to get maximum torque, gamma need to be 0, right? Cos gamma need to be 0. What does cos gamma need to be 0 means? Current I must be in phase with EA, right? So to get maximum torque, we want current to be in phase with back EMF, which is actually the maximum torque per ampere condition for cylindrical rotor machine, right? That's why you want ID to be 0. What does ID to be 0 means? That means I is equal to IQ and it is in phase with your back EMF and you are getting maximum torque with minimum current. That is what is MTPA. Okay? And we can do that by controlling the current and its phase angle gamma. So to do current control and current angle control, you can't do that with a PWM inverter like this ones easily. Okay, you have to then have some current controllers, and currents are in AC currents, right? So you will need PI. If it is PI controller, it cannot handle AC quantity properly, right? So you have to then go for maybe some PR controllers, the proportional resonance controller, and it could make things complex because current control, AC quantity control is not so easy. Okay, and so this current control is in fact used in the BLDC motor very much. Okay, the simple BLDC motor, how they do torque and speed control, in fact by this, they simply control current I and gamma with some simple methods. Okay, the proportional, maybe they will do the current proportional to torque, have a lookup table and try to get that current, and that's how cheap motors, when they have speed and torque control, this is what they do. Okay, in high performance motors, if you want to do this type of current control, you actually may need current source inverter. The voltage source inverter may not be able to do it properly. Okay, so for PMSM in traction drive, we cannot actually use this simple method. For P by F control, we cannot do because it is steady state and it cannot handle the transient condition. For simple current control like this, we will need complex PR controllers, plus still it may not guarantee good dynamics. Okay, so that's why we can't use it for traction drive applications. Instead, in fact, if we do this current control, we can also do flux weakening, right? If we make the current coming to the second quadrant, we will get a negative ID, which will be producing a flux opposite to the PM flux. This will produce a negative flux, and this is your lambda PM, so your resultant flux will be reduced. So with current control, we could do flux weakening as well, but as I said, the issue is how do you control the AC current easily? Okay, how do you make and it is again, because it's based on the steady state equation, it does not provide you the best dynamics during the transient condition. So if we don't control the transient, this is what you can get, right? We want a smooth drive like this all the time, whether you are accelerating or decelerating. But if we are not controlling properly during this transient condition, if we use a P by F control or the current control based on steady state equation, we have no control during the transient. Okay, and in reality, in real world application, this is what will happen to your EP. Okay, it will start jerking, vibrating, and obviously you do not want that, those sort of things, right? So how do we then handle the transient response as smoothly as like what we want here? This leads us to the more advanced controllers such as the field-oriented control, okay, or the direct torque control, okay, yeah, or the model predictive control. Yes. Which one? P by F. Yeah, usually P by F is an open loop control. Sorry?
You need the theta position.
So for this one, if you do V by F, you don't even need theta position because we are not doing DQ, right?
We are doing directly.
We are only need to know the speed. Okay, so if you know you may, for that you may use encoder because you want to know whether it is following this speed or command or not. But you are not controlling the speed as a closed loop. So you in fact don't even need encoder if you want to do this.
How can we forget which phase we have to excite for the starting?
So this is which phase to excite. That one you should know beforehand, right? Because you excite all three phases together, right? In this PW, it's not that you excite A phase first, B phase first, or C phase. Not like that. You already know where is your A, B, C phases, which one is. So you don't need, okay? V by F control or in this current control one. Sometimes this is also referred as I by F control. Sorry, I'm going the wrong way. This one here. This control is referred sometimes as I by F control. Okay, and the other one is called V by F control. Okay, so I by F or V by F control does not need encoder information. Okay, and they are good for some like small applications. Okay? They are fine, you can use them. Only issue is that they cannot handle transient condition and they may not give you perfect speed or perfect torque that you want. Okay? So because it's open loop control, right? So you are not controlling them precisely. In fact, like for sensorless control, many times sensorless control doesn't work at zero speed often, okay? Because the position is estimated based on the EMF, right? So at low speed you have nearly zero EMF, so you have no way to estimate position accurately. So for those type of application, at the start they usually use I by F control or V by F control just to start. Bring the speed to a minimum value from where the sensorless control can start. Okay, so even though in PMSM we do not use V by F control for whole thing, but sometime in sensorless control they are used to start the machine. Okay, but I think in traction usually we don't use sensorless yet. Okay. So, as far as I know, I think it's mostly FOC they use, not I by F or V by F, but many other applications like the high-speed motor that I talk about. So we use that sensorless control. So to start that motor, actually, we use I by F control just to start it up, to bring it to the minimum level so that I can start using sensorless control. Okay, so it has its own advantage, but not for a high performance application. Okay. So just before we move to field oriented control further, this is the structure you should remember, what we will be talking about. In PMSM, we don't have this diode bridge rectifier, obviously. In a traction application, you will have the battery instead. Okay. So you could have the battery here. You may have some kind of a boost converter as well, depending on what is your battery voltage, what is your battery rating. You may or may not have that DC converter in between, DC-DC converter, okay? And then we have this 2-level 6-switch conventional 3-phase inverter. The controllers that we are talking about, whether it is V by F, I by F, or FOC, anything, so it's here, okay, this controller, which is in a microprocessor. I think some of you got exposed to how this works, right, in the lab last night. right? So that's in the lab, but in real world, these controllers will be sitting on a microprocessor, which is part of the inverter actually. Okay, it's just a very small chip or a card. Okay, C3000. What you have in your lab? The microprocessor. Sorry. C. C2000, right? So C2000, in fact, they use something similar in the real world, because in the real world they don't have micro box or displays, right? They have to use some kind of a card like that. Okay, C3000 is the microprocessor. So it will be a simple, some like powerful enough, but small enough to be integrated in the inverter itself. Okay, that's how in real world it happens. Okay, all the controller sits on that microprocessor, and output is the PWM, which will go to your switches. Okay, that's how in the real world it is handled. Nowadays, nobody builds hardware PI controllers. Okay, if you use PI controller, it all sits on the microprocessor only. And then just to remind ourselves, so we could use PWM as sinusoidal PWM, or we could use SVM. Mostly in traction drive, space vector modulation is used, okay, not sinusoidal PWM, because you can utilize more the DC bus. So in a SVM, you can use or you can utilize up to 57.7% of the DC bus compared to 50% of the DC bus in a sinusoidal PWM. Okay, because of that, SVM is preferred for high performing drive applications such as traction. Okay, and so what's the difference? I am sure all of you know PWM as PWM. The SVM, the difference is that you're still going to get these pulses, but these pulses durations are calculated, right? That's what the SVM does, space vector modulation. We have 6 switches. Based on how which switch is on, we can get total 8 space vector. We also mentioned what the space vector is, right, last time. So you can get total 8 space vectors. Out of those, when all 3 bottom switches are off, or when all the top switches are off, you get the 2 0 vectors, okay, and others are active vectors because they will have certain values related to VDC. And those 6 active vectors can be plotted in a real and imaginary number plane, which will give you this hexagon. Okay, so each node of this is actually based on the switching states. Okay, so if I want a voltage factor or a space factor at all time, where these and each of these 6 sections is defined as sectors. So your voltage factor required by the space factor required by the motor can sit in any one of these sectors. And let's say if it is sitting in the sector number 1, this sector as shown here, to get this voltage factor, one of these 2 space factors must be activated. Okay, so that you can get the resultant vector here, right? Now, in the space vector modulation, you simply try to calculate how long, let's say we call this as 1 and this as 2, how long vector 1 and vector 2 need to be on. Okay, so that's, and that way you calculate, okay, the time required for each vector to be on. So here you can see, like for example, let's say this is A phase, get this pulse, we are, let's up to here, we have 0 vector, vector 1, vector 2, and vector 7 are required, okay, to create this pulse, okay, half of this pulse, let's say. And so we V0 need to be turned on for certain time, and V1, V2, and V7 need to be on for some other times. So that the space vector, just try to calculate that, okay, for each phases. It's kind of an algorithm, and it's a very well-known one, so you just can use what has already been developed there to get your SVM. So either one, PWM or SVM, in each case you need a reference voltage. In case of SVM, this is your reference voltage, right? In case of SPWM, this is your reference voltage. Okay? So either case you will need a reference voltage input to this SVM generation, SVM pulse generation or SPWM pulse generation. Okay, so input is this reference voltage, and this reference voltage must come out from your controller. Okay, so controller's main purpose is to produce this reference voltage basically, and after that it is simply generation of the pulses, right? Let's look at the FOC, general one. We could usually will have a speed controller and 2 current controllers. So I think you have also went through the hierarchy of the controllers, right? Why the speed controller need to be outer loop and why the current is inner loop, right? So it's a cascade control system. And you may note that now the torque equation we are using here is completely different. Okay, it's not the one we have seen in the previous slides, not the classic torque equation. So where does torque equation come from? Transformation, right? So you have gone through the transformation as well. So what's the advantage of transformation also, I think you have learned, right? The DQ transformation or inverse of the DQ transformation is part and parcel of your FOC. And that's why these transformations are matrix, right? If you remember, it's a cos theta sin theta matrix. So for that matrix, we need the information of theta. And that theta comes from your encoder. Okay? And that's why you must have the encoder. Okay? If you are doing FOC with sensor, that means you must have an encoder. If we want to do FOC sensorless, we can do it, but then you have to estimate this theta by some means. We can still do FOC sensorless. Okay? FOC sensorless is possible, but this theta then you must somehow estimate. Okay? We'll discuss a bit more, like how it works, maybe tomorrow. And then look at the DTC. So DTC again, the main difference between DTC and FOC is that in FOC you have the speed controller and then you have the current. So you are controlling current, not the, even though you want a certain torque. Your main purpose is to get certain torque, right? So you are controlling current, so you are indirectly controlling the torque. Whereas in direct torque control, your command could be a torque. You could have a speed controller here. Output of that speed controller will be torque. Okay? And the other component is flux. So in FOC, we have this torque but we are controlling this torque via this IQ current. And we also actually have flux control here, but the flux is in this case controlled by ID current. Okay, so we are doing indirect torque and flux control in FOC. Whereas in DTC, your command is a torque, and torque and flux are direct command to your controllers. Okay, and the classic DTC actually does not use SPM or PWM. They use switching tables. Okay, and using the switching tables, they just turn on and off the switches according to that table. Okay, so that table is very important. The whole thing can happen actually in the alpha beta reference frame or stationary reference frame. So you do not need an encoder to do a DTC. Okay, so it is inherently a sensorless scheme, DTC. You do not need encoder. Okay, but then you may ask me, why then we don't use DTC all the time, right? What's the issue with DTC? The main issue with DTC, the classic DTC, is that because it is switching table based, so you are not producing this vector, the space vector, continuously. You are actually producing these space vectors discretely. So because you are producing them discretely, so that leads to high torque ripple and flux ripple in the system. So you get very high torque ripple, especially, which is troublesome for high performance applications. Okay, high torque ripple means noise, vibration, etc. Right? So that's the issue with classic DTC, and there are solutions which we'll be talking tomorrow maybe. And the last one we will be talking about tomorrow is the model predictive control. Okay, model predictive control is kindly new, or PMSM, kind of new, and it's actually in this type of technique that current is predicted, and using this predicted current, the switching signals are generated based on a cost function. Okay, I think next part of the lecture you will be exposed to what this model predictive control means. Okay, again, for model predictive control, since we are not using PWM or SVM, it is discrete switching signals going to the inverter. So same problem, large torque ripple and large ripple in the flux. Okay, so that's in the classic model predictive is the same problem as DTC. Okay, so we'll be looking at some solutions for these controls tomorrow, and we'll be going more deep into the field-oriented control of PMSM in the next tomorrow's lecture, which will then wrap up this course. Okay, thank you. Yeah, should you stop? Okay, all right. So we'll stop for today. Yes.
What's the power density of the motor that you have that 7 centimeter motor?
Oh, okay. I think the kilowatt per kg, I remember, is about 6. Okay, but kilowatt per liter, I can't remember exact value, but it is pretty high, as you can see the size. So I don't remember the exact figure at the moment. Okay, yes, it is very, very high, dense motor, power dense and torque. Power dense motors, not torque dense, because it's low torque machine. Okay.
This type of motors are usually employed in the high gears, so that
So this type of motors, the high speed motors, are for conditioning systems, and for example in data centers, okay, or even in the large buildings, shopping centers, etc. You have very large air conditioning system, right? HVAC system. So the compressor that they use, if they can use high speed motors as a drive motor, they can reduce size. Okay, the whole HVAC system would be minimized. Size can be minimized. So that's one of the application. The other application is flywheel. Flywheel energy storage. They want high speed so that they can reduce the size as well as can get because in flywheel it is the energy, mechanical energy is stored, right? So it is half J omega square. So higher the speed, the more energy they can store. So they want as well flywheel applications. Other application is like you may be hearing about hydrogen to be used as a fuel. So they're talking about using hydrogen directly in micro turbines to produce electricity. So again, micro turbines uses very high speed machines, generators in that case. And many other applications like drills, mechanical drills uses high speed motors, dentist drill uses high speed motors, and so on. So some applications, some particular applications goes for this type of high speed, with or without gear. They may use gear or they may go for direct.
Second question is regarding, since it is very high speed, the mechanical design would have been very complex.
Yes.
What
So-
are the issues?
So mechanical, that's why the mechanical design become part of the optimization, as I have mentioned. That's why it become multi-physics optimization, right? So for mechanical, because you are riding at a very high speed, so the rotors needs a very high mechanical stress, shear stress, right? And the grease in IPM machine, the grease are very thin, right? The grease on the top of the magnets. So they can easily break. That's the biggest issue for IPM machine not going high speed. And our design, what we did is how to strengthen that iron grease doing certain things. Okay, so that was the invention there. So magnet topology was designed in such a way that it can distribute that mechanical stress and make that thin bridge not to break. Okay, you can make the bridge wide to make it mechanically robust, but then you will be wasting your magnets because a lot of magnet flux will leak there and that wide bridge. That's not a good design, right? So we try to keep it thin but making it mechanically robust by designing the magnet structure in such a way that the mechanical stress is distributed uniformly, not just concentrated on the bridge. Okay, that's how actually the problem was solved, the mechanical problem.
Madam, did you employ solid core or laminated etc.?
Laminated. That's the thing. Like solid core, anyone can make it. It was laminated and used conventional, commercially available material. Some people could also use exotic material of very high mechanical strength, but those material may not be easily available, right? So what we did is commercially available material and without no sleeve. We did not use any kind of sleeve to make it additional sleeve to make it robust. Just use that iron part as its sleeve for the magnets, but make that iron grease mechanically robust. Okay. Yeah. All right. Any other question from anybody? No. Okay. Yeah.
Can we apply what's the DFI control to PMS directly?
You can, but it doesn't usually perform well. As I said, like P by F you can apply. It's not not an issue. It will start. It works, but you may get.
But the current drawn is very high, ma'am. The position will not correctly match. The current will drawn will be high, ma'am.
Yeah, that's why the performance will not be good, right? It even could like vibrate. You may get noise, okay? Or it may not be operating with the torque it can produce because you are not controlling the torque as a maximum torque per ampere, right? So it is drawing very high current, as you say, because it's trying to produce a torque based on simply the V by F ratios, maximum torque, right? But you are not controlling anything. It's open loop, right?
But the speed also, when I assume the speed will be clockwise, but it will rotate in anti-clockwise because of the position.
It may rotate both directions. I don't think
because of the position, it will wrongly rotate in my experiment.
It depends. I mean, in your case, it's right, but if it may not. It is like we cannot make a general comment that it will always rotate in anti-clockwise. It's not a general comment. Maybe specific to your setup, it was doing that. But the problem is that it may not be able to produce the torque that it can actually produce, right? If we do V by F. So, like for an experiment, like in our I think undergraduate courses also, they do some experimental V by F control of the PMSM just to understand. So it works, yeah, it does work, but you don't get the best performance out of it.
But you tell that what you design the model, it will start from V by F, then it goes to
So that is in the sensorless control. So in the sensorless control, usually it's very hard to start them from zero speed without any sensor, okay? Because at zero speed, you cannot estimate the position accurately enough, right? Because the position estimation is either based on the back EMF, mostly back EMF, or sometimes it uses saliency, right? But to estimate position at zero speed with saliency, you need to in fact inject high frequency signal. Okay, only with high frequency injection, the position can be detected at zero speed. So you have no option to start the machine from zero speed, right? If you're not injecting high frequency, there's no option, right? And sometimes even high frequency injection may not be allowed because injection of high frequency can cause again extra loss and extra vibration. So some application you don't have that option. So in that case, how do I start? But I still have a sensorless control. I don't have an encoder. Okay? For my high-speed test bed, I don't have an encoder because the encoder cannot work at that high speed. Okay? We do have an encoder, but it is like very noisy and things, so we just did not use it.
But the differential differential signal is there, that will get the noise in encoder.
Whose differential signal?
Differential signal. Nowadays encoders will be like A plus and minus.
Yeah.
And if the noise will be like that
Yeah.
signal will difference.
So, but the encoder is kind of a mechanical device, right? So they need to also be robust enough to go to 100,000 RPM. So there's no such encoder. So we could not use the encoder for the high speed. So we bought one. It could work up to I think I don't know 40,000 or 30,000 or something. So, but it was not good, very good because it is making a lot of noise. So we ultimately decided not to use it. So now we have the problem of how do I start it, because I have no signal and at zero speed high frequency injection can be done, but like if I don't want to do that, then there's no option for me to start the motor. So for that we actually use I by F. Okay, you could do P by F, but we did I by F because I by F is a little bit more accurate, or you have a little bit more control because you are injecting current rather than voltage, so you have the control on your current. So if we don't control the current for magnet motor, it's also risky whether it is going to demagnetization if you push too much current, right? So that's why we did I by F, and we are able to start it. And once it So,
Synchronism.
sorry?
Synchronism will come after.
Yeah, so after some times the sensor will start to give us the accurate position, and then we just move to the sensorless control, FOC or whatever control we are doing. Okay, so then we do the sensorless operation. So then during starting, that's why it's V by F, I by F is quite good technique to use. It's very simple. It does not need editing, so it's good. But for the full range of operation, it's not recommended. Okay.
Ma'am, what is your suggestion to start a PMSM? Whether I use VFD drive, the technique that you are saying I use V-bias control or damper winding for FOC or ETC. What is your suggestion?
So if you have censored encoder, you have no problem starting, because if you have encoder and if you are doing FOC, V and F increases in proportion. So if you have zero speed, means your frequency is zero, voltage is zero. Next, let's say you go to 1 RPM. So 1 RPM, whatever the equivalent frequency, and you increase the voltage equivalently, right? So this happens through your FOC itself directly. Okay, so that's why you don't need this damper winding. Neither you need this sort of V by F or I by F or startup. Okay, it will start automatically. Okay, if your FOC is working properly. It's just how good your controller tuning is. If you tune your controller nicely and perfectly, no problem with startup with sensor. Okay?
You said that in position sensor there is a noisy. Can you give me that after this value the noise will effect of noise is very.
After which?
After one speed the position sensor will affect the noise. If 1000 RPM is there,
Yeah.
so maybe noise is too low, so
Yeah.
we can eliminate it.
Yeah.
But after one more point of speed, the noise will become very large.
So it depends on the encoder specification, right? Your encoder data sheet should tell you up to what speed it will give you the best resolution. If it was designed for, let's say, 1000 RPM and you try to use it to 2000 RPM, maybe then its resolution becomes poor, right? And then that could cause problem for your FOC as well, because your FOC completely depends on your encoder theta signal, right? But if it is designed for 2000 RPM, it should not give you noise. Okay, it will have a cutoff filter somewhere in their design itself, so it will eliminate all the noises. That's what we have seen. If the good encoder, they will work. Okay, up to whatever speed they are designed for. Yeah. Okay, and you can always have on top of that, if you, for speed signal, so speed controller, you can have a low pass filter if you want. You can always add a low pass filter. Okay, even outside of your encoder, low pass filters, but go for some software low pass filter in your control, not a real hardware low pass filter. You don't need to. Okay? There are lot of nowadays small codes you can write which behaves like a low pass filter, and use those things, that are cheaper, don't need any hardware, and it just becomes part of your control. Okay.